Now, in the last video, we talked a lot about, when we talked about hypertensive nephropathy, we talked a lot about how the glomerulus of the kidney is exposed to very high pressures. And of course, this is an adaptation to allow the kidneys to make an ultrafiltrate. Under pressure, we are extruding plasma from the glomerulus into the Bowman's capsule, which goes into the renal tubule. Now, one of the adaptations that allows our glomerulus to withstand those pressures is the fact that we tightly regulate those pressures by vasoconstricting and vasodilating the arterioles on both sides of the glomerulus. So again, having smooth muscles and the arterioles on both sides of the glomerulus allows the kidneys to have exquisite control and provide a very narrow range of pressures within the glomerulus, between like 50 to 70 millimeters of mercury, whereas systemically, the range of pressures between within the systemic capillaries is going to be much wider. Now, I want to introduce now another adaptation that the kidneys have, that the glomerulus has, to withstand these very high intracapillary pressures. And this is called the mesangium. The mesangium is a collection of cells, or a small bit of tissue, that sort of lays in the middle of the glomerulus, the tuft of capillaries, and it provides some structure. Now, these cells are actually part of the capillary structure, so if you kind of look at an end-on view of the capillaries, what you'll see is, on the inside, you'll have your endothelial cells, and then, well, this basement, the red will pretend as a basement membrane, although it's much thicker than it would be. And then, obviously we have our podocytes on the outside. And so there's our little podocyte there. And then sort of off to the side, if you can imagine that we're sort of looking at the middle of the tuft of capillaries here, we have some mesangial cells. Now, these mesangial cells are actually relatively closely related to, they have the same lineage as smooth muscle cells, but they aren't smooth muscle cells. They don't have any contractile components, no actin and myosin. So these are mesangial cells. And this section here is called the mesangium. Actually, to be more specific, this is called the intraglomerular mesangium, because there is actually another mesangium that is outside the glomerulus that is part of the juxtamedullary apparatus. And they're similar cells, but they have a different function. So we're talking here about the intraglomerular mesangium. So what do these cells do? Well, one thing that these cells do is they actually create this collagen network that holds all the capillaries in place. And one of the things that these cells can do is they can actually cause this network of collagen fibers to sort of constrict or dilate, so they can pull the glomerulus tighter together or allow it to spread out. And this seems to cause changes in the fenestra, so the mesangial cells can sort of allow more filtration or less filtration by constricting or dilating. Also, the mesangial cells have the ability to secrete cytokines. in reaction to sort of stimulate inflammation in reaction to injury or other chemical mediators. So they play an important role in sort of a central role of the immune system within the glomerulus. Okay, so that explains the normal functioning of the mesangium, the mesangial cells. Now, the mesangial cells play a very central role in the pathogenesis of diabetic nephropathy. So what we know is that these mesangial cells are going to respond in diabetic nephropathy, respond to sort of two inputs. One is increased pressure and barotrauma. And the other is injury from the free radicals that are released due to high BGs, high blood glucose. So everybody knows why. We talked quite a bit about diabetes, and everyone's got knowledge about why diabetics have high blood glucose. But why do diabetics have high glomerular pressures? Well, of course, one reason is many diabetics have hypertension. It's part of metabolic syndrome, and they often coexist. But the other reason is many diabetics have high insulin levels, particularly type 2 diabetics that still have a functioning pancreas. They're trying to make up for the increased for the insulin resistance and the increased blood glucose levels in their body by increasing the amount of insulin. So they have hyperinsulinemia. So hyperinsulinemia is one factor. And there's a number of other hormones and chemicals involved here. But suffice it to say that even if a diabetic has normal systemic pressure, they oftentimes will have hypertension in the glomerulus because many of these mediators, like insulin, some other hormones, and some cytokines, angiotensin is one of the central ones, causes vasoconstriction of the efferent arterioles, and that raises intraglomerular pressure. Okay, so this is increased intraglomerular pressure. So we have barotrauma or free radicals that are causing stress to this mesangial cell. The mesangial cell is going to react in a couple of ways. First of all, it's going to release cytokines, and that's going to cause inflammation. And second of all, the cells are going to stimulate a hypertrophy of the mesangium, otherwise known as, if you read in the literature, you'll often come across the term mesangial expansion. And this is, essentially hypertrophy of the mesangium, where we have cells that are larger and greater in number. Now these two factors are going to combine together to stimulate the mesangial cell to start to create an increased mesangial matrix. Remember, the mesangial matrix is this matrix that the mesangium creates around itself that holds the capillaries together. So it's going to thicken this matrix, right? And what is this matrix made out of? Well, fibrin, collagen. Now, with increased fibrin and collagen within the glomerulus, we're going to start to have glomerular atrophy and dysfunction. Okay, the glomerulus will eventually become completely useless, and Bowman's capsule will be filled with fibrin and collagen and no longer be capable of filtering and beginning the process of.
A continuación les presentaré las etapas de la nefropatía diabética. Estadio 1. El estadio 1 es una etapa que se caracteriza por cambios tanto funcionales como cambios estructurales. Cambios funcionales porque el paciente aumenta su tasa de filtración glomerular, es decir, hiperfiltra. Y cambios estructurales porque el paciente presenta nefromegalia, es decir, un aumento del tamaño del diámetro renal. Esto es un cuadro que tiene alta reversibilidad, por supuesto, siempre y cuando el paciente tenga un control metabólico óptimo, con reversibilidad aproximadamente de 3 a 6 meses. El estadio 2 se caracteriza porque se presenta de 3 a 10 años después del diagnóstico. El paciente persiste con la hiperfiltración, aparecen las primeras lesiones histopatológicas características del aumento de la membrana basal glomerular y la proliferación sanguínea. Regularmente estos pacientes no cursan con hipertensión, sin embargo tienen pérdida de la condición hipernocturna, lo que se sugiere una monitorización ambulatoria de 24 horas. Acá pues pueden observar el incremento de la membrana basal glomerular por microscopía electrónica. El estadio 3 es una etapa que se caracteriza porque se presenta 10 años después del diagnóstico. El paciente inicia con microalbuminuria en un rango de 30 a 300 miligramos gramos. Por supuesto, mayor lesión histopatológica, ya es un cuadro totalmente irreversible y puede encontrarse retinopatía o neuropatía diabética. El estadio 4 se caracteriza porque se presenta de 5 a 10 años después de la aparición de la microalbuminuria. El paciente tiene pérdidas importantes urinarias de albúmina, además cambios histopatológicos importantes como una hialinosis arteriolar y glomerulosclerosis difusa. El paciente está hipertenso con una función renal deteriorada. El texto describe que la tasa de filtración glomerular desciende aproximadamente 1 ml minuto por 1.73 metros cuadrados de superficie corporal de manera mensual. A continuación les presentaré una imagen histopatológica de un paciente diabético de larga data por microscopía óptica de luz, donde se evidencia una glomerulosclerosis intercapilar nodular, o también se conoce como enfermedad de Kismet-Wilson. Y la última etapa, el estadio número 5, se caracteriza porque se presenta 25 a 30 años después del diagnóstico y afecta a un tercio de los pacientes con enfermedad renal crónica que ameritan, pues por supuesto, terapia de soporte renal. Entonces les presentaré a continuación las lesiones histopatológicas según el estadio. El estadio 1, un riñón normal. El estadio 2, entonces un riñón nefromegálico con aumento de la membrana basal glomerular. Estadio 2. En el estadio 3, entonces un riñón con una glomerulosclerosis difusa. En el estadio 4, entonces el paciente tiene una glomerulosclerosis nodular o enfermedad de Kismet-Still y Wilson. Y el estadio 5, entonces el paciente ya presenta una nefropatía terminal. A manera de resumen, les presento a continuación la historia natural de la nefropatía diabética. Acá ustedes pueden observar en el eje de las abscisas los años, en el eje de las coordenadas, en el extremo izquierdo la tasa de filtración glomerular y en el extremo derecho lo que es la albuminuria. Tanto en el estadio 1 y 2 el paciente está pre-nefrópata. En el estadio 3 hay una nefropatía incipiente. En el estadio 4 hay una nefropatía establecida y en el estadio 5 hay entonces una enfermedad renal crónica. ¿Qué pasa? Acá ustedes pueden observar que la tasa de filtración glomerular, ¿sí? En el estadio 1 y 2 el paciente hiperfiltra, en el estadio 3 se la conserva, pero en el estadio 4 empieza a deteriorarse la función renal con descenso importante de la tasa de filtración glomerular. Sin embargo, en relación a la albuminuria, en los primeros estadios no hay pérdidas urinarias de microalbuminuria, pero en lo que es en la etapa 3 y 4 inicia progresivamente las pérdidas de proteínas urinarias.